the whole quest in science of, trying to discover new things. I'm a builder. So, if I have some goal in mind, build an instrument or new measurement technology, quantum computer, and then trying to figure out what we need to know. And I would say in the end, it's kind of asking the right questions that kind of get you motivated to go in the right way. And I found that just to be a fascinating part of my journey.
Just a huge privilege for me to be speaking with you as someone whose work I deeply admire, and obviously whose work has been recognized with the Nobel Prize. And I just a few years ago, I never imagined that I would be speaking to people like you. So it's a huge honor. And last year in 2025, you, along with two of your colleagues, received the Nobel Prize in physics. And maybe if you could describe in more detail what was the discovery about, and kind of its implications, for things like quantum computing, because I know it became a foundation basically, right, for quantum computing, and because I think it's so important and such a significant discovery that you and your colleagues have made, and no surprise that it has won you the Nobel Prize. But maybe if you could describe in more detail what's that all about for us.
Yeah. Sure. Let me just start that it's a great honor for the Nobel Prize, especially since these experiments were for my thesis experiment in graduate school. And, it was really wonderful to have John Clark as my advisor, and also working with Michel Deveray, who's a very special scientist. And I would say I got interested in this idea of seeing quantum mechanics in electrical circuits because John Clark was doing some experiments looking at quantum noise in these electrical circuits. So he had been doing a little bit of this, and that really fascinated me because as a student, you're fascinated by quantum mechanics. And also my hobby was electronics. So this kind of combined my hobby and this deep fascination. The experiment was very much motivated by Professor Anthony Leggett, who unfortunately passed away about a month ago. And he was motivated to kind of bring up this idea. Actually, let's just say from the Schrödinger cat paradox, where in the Schrödinger cat paradox, you have this microscopic system of an atom that decays. And then if it decays inside of a box, it kills the cat. And you set it up so that, half the time before you open up, the cat would be dead, half the time alive. And then you're presented with this problem that is this Schrödinger's cat in a superposition of dead and alive. Now, what, there's various ways to think about this, but what Professor Leggett very cleverly understood was that there really was no evidence that macroscopic variables could obey quantum mechanics. It had not been demonstrated yet. Microscopic systems, sure, lots of them, but for macroscopic, not. And then he proposed the superconducting Josephson junctions being a macroscopic device made of many atoms, electrical circuit you could see with your eye. And then he proposed this macroscopic quantum tunneling as the way to look for quantum effects. And the basic idea is you make this circuit with what's called a Josephson tunnel junction, which is a weak link. And then if you have small amount of current flowing through it, it's in the superconducting case. If you put enough current in it, like all superconductors, it kind of breaks the superconductivity and it goes normal. And then the transition from the no voltage to voltage state is then you can think of it as a macroscopic thermal activation is a standard uh, escape from a barrier, escape from a well problem. Thermal at high temperatures, and then quantum mechanics at low temperature, quantum tunneling. And then the experiment was just to, observe that. And then besides taking, what was really new in the experiment that enabled us to do it so well is we figured out we had to do very good filtering to get rid of all thermal noise, which would mimic the quantum tunneling, measure the parameters by really doing good microwave engineering on that, which kind of combines microwave engineering with quantum mechanics in the right way to put them together to understand that. And then we observed, you know, conclusively that it was tunneling. And also, we would drive the system with microwaves and see the energy level quantization, which is really kind of the smoking gun. This is what the quanta of quantum mechanics means. You see that phenomenon, and then you really have proved to see quantum behavior. So this was very nice at the time and answered this basic question. But of course, it became important because people were thinking about quantum computing for, let's say, the first 10 years. We're just studying the physics of these quantum devices and started opening up a lot of research by people around the world. Eventually, you looked at the quantum computing applications. And now, I don't know, there are probably thousands of people around the world looking at that. And thus, that experiment kind of laid the foundation for looking at that. And I would say at the time, it was kind of a little murky about how to think about it exactly. And then by putting it on the foundation of understanding the microwave engineering and the like, and then filtering and doing the experiment in some careful way, we really put the foundation in that people could do more and more complex experiments. And of course, over the decades, many, many people have contributed to building a quantum computer.
It's fun to ask this kind of question because I'm sure you've got still some fresh memories. It happened not too long ago, like when you went to Sweden to receive the Nobel Prize, right? What was, if you could describe for us, what was the experience like? Maybe what memories, stand out to you the most? And yeah, I'm sure like it must be a lot of fun, doing this kind of stuff. But maybe there were some things that stuck with you the most. Yeah, maybe you could.
So let me just say that as a scientist, your joy, the thrill is doing the science, discovering these new things, writing about it, giving talks, explaining it to people, seeing other people develop ideas, and just bringing up the science of technology. This is just fascinating. And I would say the biggest thrill of my career is just seeing all that develop over time. And to be recognized with the Nobel Prize, of course, is a very special event. It was, kind of unexpected. It had been a long time. You kind of know this might happen because the Nobel Foundation puts on little workshops where they talk about the different fields to know the fields better, know the people involved, which is a really good thing. I would say that's the most reasonable honor you can expect to be invited to that. That's a fantastic honor. And then in the end, to get chosen for this is really great. So going to Sweden was just an amazing event. Um, they kind of treat you very special. They kind of treat you as a diplomat, starting when you arrive on the airplane and you get into the special car, and they treat you right. They have a whole schedule. A diplomatic attaché is with you the whole week, kind of explaining that. And the way I kind of think about it, I thought about it afterwards, is they're kind of training you to be a science diplomat. with all the different events you go to, a meeting with school children, meeting with the press, giving your lecture, then the ceremony and the city hall banquet, and meeting the royal family of Sweden. It's all just a really amazing experience. And I kind of think of it as training to be a scientific diplomat, if you want to do that. And that's actually been the fun part of it, is talking, especially to young students. It's quite interesting, but also giving the podcasts and talking about this. I really kind of enjoy it, and yeah, that's a real honor to be able to represent science, represent physics, and represent quantum computing too.
As you mentioned before, your work has been really foundational to modern quantum computing. So, kind of a natural, follow-up question then would be, if you could explain what a quantum computer is, because I'm sure like it's a question that you've been asked 1,000 times, but everyone seems to be talking about it these days,
Sure.
about quantum computers, and because as I know you've been working on building those yourself, right? You start your own company a few years ago, and yeah, maybe it would be great to hear about it like firsthand from somebody directly involved in that kind of effort.
Yeah, so the simple explanation, but gets you to the heart of it, is that, well, first of all, computing is important for, life. As we're seeing right here, it enables us to do many new things. And then quantum computing is just a new way to do computing. Because of the laws of quantum mechanics, you can compute in a more general way than you can do with classical compute. And for example, in classical, you have bits that are either 0 and 1, and you string them together to make words to represent data. And in quantum computing, it can actually be in a superposition of 0 plus 1. Okay, and what's interesting about that is it allows you to take this 0 plus 1 state, run it through a quantum computer, and get the answer of 0 and get the answer of 1 kind of at the same time. And then what happens is you string the qubits together, let's say 2 qubits, you're then parallel processing 00011011, 4 states. 3 qubits is 8 states, 4 is 16. And the amount of this processing goes up exponentially. So, by the time you're at 50, the parallel processing is rivaling that of a supercomputer at about 300 qubits. That's a number that's bigger than the number of atoms in the universe. So you're clearly doing something. A little bit more precise way to say that is that you have an enhanced instruction set when you have a quantum computer. So you can go to the 0 state in a classical computer, the 0 state to a 1 state, which is a NOT gate. But with a quantum computer, you can go from the 0 state to the 0 plus 1 state, which we call a square root of NOT operation. This doesn't make sense classically, but quantum mechanically, you can do that. And because you have this enhanced instruction set, you can build new kind of algorithms that take advantage of the instruction set, but only for certain classes of problems. It's not like every classical problem can be sped up with a quantum computer with a parallel processing. That just doesn't work. Of certain problems. And, for example, one of the problems that, I think about and I'm motivated at is solving quantum mechanics problems of quantum chemistry and quantum materials. And there's a mapping between the quantum mechanics of how you solve electrons and atoms and molecules to a quantum computer. And, that's been a really nice application. And I would say what I find interesting about that application is that simulation is extremely important in our rule. You design electric circuits. My wife designed the kitchen. We built a couple years ago, and kind of test it out before we actually build it. And you want to do the same thing when you do chemistry for materials and molecules. And you can do that now to some degree, a good degree, with classical computers, but it's very hard for the same reason a quantum computer is powerful. And if you can do that much better with a quantum computer, then you could more easily invent chemistry processes and the like. And I think that's a really compelling application. And other applications for data processing too.
What I also find fascinating is that when you're, for example, doing those experiments in the, I guess, 1980s, right? As a graduate student, you could not have perhaps possibly foreseen the impact that your work, right, would eventually have. Inspiring people to pursue building those quantum computers, and perhaps you didn't expect that it would win you a Nobel Prize either, right? And so, it's just amazing to me that this kind of basic research, it can yield some amazing technological developments, and that's why it's also so tragic for me to see those cuts in funding when people don't want to support just basic research, because even though it doesn't it may not yield anything practical right now, but decades later it can pay off, and in a really huge way.
Yeah, and this was very much a basic physics research, asking the question, do macroscopic variables obey quantum mechanics? And, to me at the time, that was the most interesting thing I could possibly do. I don't know why there wasn't 20 or 30 other groups trying to do that at the time. But, what happens is at the time, people knew the rules for quantum mechanics. And I think people thought, well, okay, it'll just, obey quantum mechanics. But we really said, let's prove this, very conclusively. It's a good fundamental question. Let's prove it conclusively. And by wanting to prove it conclusively, we figured out how to measure parameters. We figured out how to do the microwave engineering and really think about the experiment, which then led to all the other developments. That's a very key point. But what also has happened is, at that time, asking these fundamental questions of quantum mechanics was not really popular. But since then, we've had the Bell's inequalities and all these quantum devices where we tested quantum mechanics very carefully in different ways and understand the details of it better. And that just evolved from that time onward, where people started doing, and not just cigars with ion traps and other systems. And it just became a field in itself to really understand that. Now, the interesting story about my thesis is, when I was writing up my thesis, I came to a conference in Santa Barbara on this macroscopic quantum tunneling, where they talked about this. We presented our data. But what was interesting is the last talk of the conference was by Richard Feynman, where he talked about quantum computing. So people were kind of connecting it at the time, and that's where I first learned about it. So it was a great talk. I would say I didn't understand everything at the time. I mean, it was all very new. But afterwards, he was just mobbed with people asking him questions about, what this means. And it was very clear to me, even as a young scientist, that this was a great question, a great quest, something we should do. And it's great that the theory developed in the next few years. And I would say, a lot of people development, but for example, Peter Shor and the factoring algorithm and then error correction were, for example, very important theory developments in the early 1990s that, gave people some hope that you could really build a quantum computer. And then the big event was funding was available by the US government to develop it. But it was really all that basic research, which you talked about, that was funded that led up to a more applied direction. And yeah, that was really, interesting to be part of that, working on the quantum devices for about 10 years, just understanding how the devices worked. And then when the application came, very clear in the mid 1990s, and, we could really jump on it.
What I also find fascinating is that you did those experiments as a graduate student, and after you retired as a professor, you got the Nobel Prize, right? So it's kind of it's an amazing journey, I guess all those smartphones, right, and computers. It all fundamentally relies on quantum mechanics, right? And it's amazing to me because people like Einstein, Bohr, Schrödinger, they could not have possibly imagined this when they were just asking about electrons and stuff. So it's kind of
Yeah, that's right. And a lot of these basic questions, were very important for the field. And then, of course, there were people who started thinking about quantum computation, not just Feynman, but other people who really developed the field. And, it was a lot of very nice theoretical developments to understand how to really think about this. And then, of course, you had to develop a lot of the experimental technology in superconducting qubits and other qubits, to start making that a reality. So it's been a very interesting time for me to see how this has progressed.
Could you also please tell us maybe how you got into physics in the first place? If you could go back to your childhood, I guess for you, as an experimental physicist, it was more like about building things, yeah. But maybe there were also some books that you read.
My father was born in Croatia. He went to war instead of high school. He has a GED, but he was a fireman. My mom's a homemaker. But my dad was always building these projects in the garage. He would have been an excellent engineer if he would have the educational chance. But, as it is, a fireman, that's a pretty technical job. You have to know a lot as well as the physical capabilities. But he was always building things. And the way he built things, he always kind of understood some based on some fundamental idea of how it worked. Okay, now a lot of times that wasn't the correct physical explanation exactly, but he thought about the fundamentals and how you do things. And what that gave me is a really strong background to be able to build things from, very simple materials around me. So as I grew up, I was always interested in science. I got involved with electronics through various kits and the like in high school. I remember reading a book where they explained how you design electronics with transistors, where I actually got to use my math. That was really great. But when I took my high school physics class, I really loved it. And I liked it because you were, deriving things all the time and doing the first principles. I was pretty good at this. It's funny, I have a very poor memory. And the nice thing about physics is you're supposed to derive everything, not memorize things. So that kind of deficiency in my brain, if you want to say, has been very good because the only, I just had to derive things and understand things to understand that subject. And that very much helped me. So yeah, I was just fascinated by that. I took physics in college. I was wondering whether I wanted to go into physics or computer science at the time. But I did well in physics, really enjoyed it. I've always enjoyed, computers and programming. Of course, that's what I'm doing with the quantum computer. That was kind of a natural thing to go with. But I went to UC Berkeley. I took honors classes. I loved the classes. They were taught, so well. And, for example, in my electromagnetic course, the second year, the class was taught by J.D. Jackson, who wrote the classic graduate text on electromagnetism. So I had some amazing teachers, and I just loved the subject. Just made sense. I did well in it. But of course, what I was interested in was to be an experimentalist. So I really started to take off when I was my junior year. I did experimental course, and then I started doing research in my senior year. And I just loved doing that. I just love the whole experience of trying to build these experiments.
Getting back to quantum computers, how do you envision the future of this? Do you expect that maybe in 10, 20, or 50 years, who knows how long this may take, that we all would eventually have these devices on our desks, much like we have those traditional computers, Mac or Windows, at home, or and basically those like classical computers would simply become irrelevant, much like those huge machines that used to fill the entire rooms. If you remember, from history, or those, like, for example, old phones with physical buttons, like no one uses that anymore. So do you think that maybe it would one day become affordable enough that most people would have it as
I've been through the various computer revolutions, but if you look at your cell phone, which everyone has there, it's a powerful computer in here, but it's really more of an interface terminal to the data centers where the really amazing things are happening for computing these days. That's not to say we don't use our regular computers for doing some computing, but I think the way that quantum computers are very complex, they require some unusual physics and the like. I think, at least in the near term, you never know long term, but in the near term, they're going to be in data centers and we're going to use them remotely in the way that we use powerful supercomputers these days. So I kind of think that that's the way it's going to be. But I'm hoping, after you do the initial useful applications and develop it over the years, that, when you do a search or you want to do some other things with your phone, you're going to be using some kind of quantum enhanced data manipulation in a data center to help that work better. So I think that's the more likely thing. Now, of course, right now, what we've done is we've built powerful quantum computers that can solve specialized mathematical problems. That was like the quantum supremacy experiment in Google that I led the hardware team on in 2019. That's nice, but people are trying to build useful things right now. And, you can think of useful as, generating real value, generating money for people. So they show it's valuable. And then that will really, enable the field to put more money in to build more and more powerful things. So that's what everyone is trying to do right now. And I think that's an excellent quest. I mean, I'm certainly thinking about it. Many other people are thinking about it. And that's kind of what we need to do for the next step.
Yeah, I also love asking people about books, if there are any that they might recommend. So I know how often you get to read books, given everything that's going on in your life. But maybe there are some that you read recently that you found particularly interesting. Maybe.
Unfortunately, I'm so advanced in quantum computing that I can't recommend an introductory book right now. Okay. And like other people, watch, YouTube and other podcasts a lot. What I would say, what is really influencing me is reading a lot about SpaceX or Tesla. These are these Elon Musk companies where they're really getting good at manufacturing, new manufacturing technologies, doing it well, keeping the costs down and the like. And I really find this fascinating because I think there's kind of a research resumption of doing manufacturing in the US, which is very good for your economy. It gives a lot of jobs. But also, if you do that right, you can really make technology available to more people. Now, what I'm interested in is thinking about this advanced manufacturing to be used for quantum computers. And right now, if you kind of take the technology we have with superconducting qubits, it would cost maybe tens of billions of dollars to build a superconducting quantum computer. And this outside the cost range for, to do something. We could see if anyone wants to put that kind of money into it, we'll see. But my company that I've started, we thought very carefully about what technology do we have to develop to make it more manufacturable, make it cheaper. And the simple thing is to say we're using semiconductor kind of manufacturing tools and processes to do that. It's more than that, but that's a simple way to think about it. And so I'm really fascinated to take these principles that, people talk about. Books have been written on the principles behind the manufacture. Why is SpaceX doing so much better as a rocket company than the established people like Boeing and the like? And take those concepts and try to apply that to quantum computing. And to me, that's a really fascinating topic. And I think, and what's interesting is, I understand physics pretty well, electroengineering pretty well. Now I get to learn kind of in my retirement years. I'm not retired, but I get to learn, well, how do you think about manufacturing? How do you think about cost? And to combine that in the whole technology development that you're thinking about. And that's really been quite a nice journey for me in the last few years to figure that out.
Well, you did some very important basic physics experiments that basically started an entire field. You started your own company, you like won the Nobel Prize, and like what else can like what else do you want in a career?
It's very simple. Okay.
Yeah,
I would like to build a useful quantum computer. If not me, I would like to help the field build that. Whoever, has the resources to do that. And my contribution is going to be on, building the chips in a new way, in a much better way, and packaging and manufacturing that. And, if we help someone else build a useful quantum computer, great. If we do that, great too. There's a lot of opportunity there. So, that's kind of been my long-term vision. And I'm really excited about figuring out how to do that. And again, I think that in order to do this properly, you have to really think very carefully about manufacturing. And in each SpaceX, Elon Musk, they talk a lot about first principles, kind of physics thinking. And I think my experience as a physicist, especially I've been thinking about systems engineering for years, I'm really in good position to think about how to do that right.
you've done a lot of great things in your life, and is there some advice that you can give to young students who also dream of doing something big?
Yeah, I'll give an example. I was working at Google, and we were very successful with the quantum supremacy experiment. But then things changed afterwards. They changed their management and the way of doing things. And I was just turning quite unhappy. So I had to leave. That was a huge change in my life. It just was very, very hard for me. It's kind of like giving up on your dream to build a useful quantum computer. But then what I did at that point is I started thinking about, what is it that I wanted to do? How did I want to build this? And in a way that would be different than what Google could do as a corporation. So I just started thinking about it and coming up with ideas. In the end, I would not have come up with the ideas for my present company if I was in a big corporation that, it wouldn't necessarily fit into that. So, you have all these life challenges and then you just move on and you just have to think carefully about things. The other thing I would say is, and this is kind of goes back to the Nobel Prize. Um, a lot of times, you just have to look for problems that other people aren't thinking about, or it's not fashionable, or the like. You have to think very carefully. It's a good idea, but if you really believe in something and you have good reasons to think it might work, then yeah, you really try to work hard on it and approach that. And that's what happened, with the Nobel Prize, and actually several other things in my career. I really did new things that people thought were not very interesting or useful and panned out. So if you want to, I'd say if you want to do something impactful, then a lot of times you just have to do something that other people just don't think makes sense. For example, the whole thing about manufacturing and building the qubits in a certain way that we're doing is not something that, most of the people in the quantum computing field is where they want to go. And that's fine with me. I want to do something because I see in the long term, if you can get it to work, it's going to be great. So yeah, keep your eye on doing, being a little bit different than everyone else. Think about it hard. There's maybe a reason why no one else is doing it, but think about it hard. And then, if you have good reasons, just keep at it. Persistence is key. But I do have something to talk to physics students, maybe in high school or college or whatever, having to do with the modern education system. And I think this could be very helpful to students. The basic idea is in physics, you learn how to do physics by doing your problem sets. You learn the concepts in, let's say, a lecture in a book, but you actually solve problems to apply it. And this is how you learn, how to do things. And one of the things students have to realize is physics is kind of a specialty science, but people want to hire physicists because you're trained to solve problems in very unique ways, maybe never been solved before, but you kind of can think about it in a unique way or solve it in some unique way. And that's what makes it a very valuable science. And I think going back to Elon Musk, he was trained as a physics undergraduate. And, you can see him doing first principles understanding all the time. Now, the thing I want students to really understand is very often now, every problem the professor can post for their homework is probably on the internet, or you can use AI for them to figure out the solution. AI is really getting good. And although this is nice for getting your homework done quickly, and you could maybe learn from the solutions, it's not the same as struggling through the problem yourself. And if you use AI to, solve your homework problems, you're really missing out on what it is to be trained as a physicist, more so than other disciplines. Let's say in engineering, you still have to do this, but a lot of times you just look up the solution and apply it to your situation and you're okay. Physics, you're really trying to do something new. So I just warn students to be careful about using AI. Try to struggle hard and, figure it out yourself, even work with friends, because that's a good way to figure it out too. I mean, okay, you want to turn it in, looking up the solution, at least you understand kind of how to get it solved. But it's the struggle of figuring out how to solve the problems that is, how you're training yourself to be a scientist and a physicist. And make sure you don't take the easy way out and, use these computer tools these days to do that.
Yeah, and
I mean, maybe there's a metaphor for life too. I don't I don't know about that, but at least for a physicist, you really want to understand how to solve problems.
maybe a good way of like paraphrasing that would be to try and figure out stuff yourself, right, for yourself, not just to always
Yeah.
like search for answers that are there, but yeah.
And that helps you in life in so many different ways. Don't just take, just you listen to the media, listen to the news, and they're kind of telling you how to think. Okay, you want to look at a bunch of news sources and kind of come up with your own view of yourself. It's the same as what they're telling you. Yeah, that's okay. But yeah, you want to be a little bit more introspective about, how to view the world.
Just a fun question came to mind for me. If you could, for example, sit with Einstein, right, and show him what you're doing with quantum computers, do you think that he would have been able to make sense of any of it? Because from history he didn't really like quantum mechanics for a bunch of reasons. Do you think that he would have been able to understand this?
Yeah, I would say, the whole, he had a real problem with quantum mechanics and God does not play dice kind of quote and the like. And that would be a nice conversations to understand, how he thinks that way, especially given all the modern experimental evidence there is on how these systems work and the like. And I kind of can understand his view a little bit, but it would be nice to talk to him to really, because he was a deep thinker, really, get to the details of, why he thought a certain way. I think that would be great.
Did you get to talk to other maybe Nobel laureates, right, from other fields? And there was
Oh yes,
something that
that
you
was
learned
very,
from.
very
Yeah.
interesting. And I particularly liked this year talking to the economic prize winners because they were talking about technology and technology development. And it really kind of relates to what we're doing right now. And the basic idea is let's just take shipbuilding, okay, which we visited the Vasa in Sweden. It's an amazing thing. But people with shipbuilding would have certain designs and they modify it a little bit to make it better in certain ways. So they had some ideas on how it worked. But like with the Vasa in Sweden, it sank because they, didn't design it as carefully as they could. But what they pointed out is once they had better physics and really understand the physics and mathematics of a phenomenon, you were able to make it better and better over time and come up with new ideas. And it was really some of the fundamental ideas you had to understand in order to move the technology, not just a little bit, but by big leaps. Okay. And, that's what I think we're doing with quantum computing right now. Although we have a lot of fundamental understanding, there are some practical issues we still need to understand. And if we were to develop good models from that, then we could really do the manufacturing and the scale up and all the things we want to do much, much better. So I very much appreciated that, and that motivates me even more to think about the fundamentals of what we're doing, as well as as we're trying to build a practical technology.
The final question I want to ask you, because I know you don't have much time left, right? And is uh, when you think of all the things that you've done in your life, what would you say has given you maybe the greatest feeling of happiness, or just yeah, what gives you like the greatest sense of purpose?
So, just in terms of like this kind of life advice, it was getting married to a wonderful woman and having children and watching them grow up and talking to them now. This is like the best thing. And, you know, I want to talk to scientists that there's more to life than science. And that these are wonderful things. But going back to science, I mean, you know, I would just say the whole quest in science of, you know, trying to discover new things. I'm a builder. So, you know, if I have some goal in mind, build an instrument or new measurement technology, quantum computer, and then trying to figure out what we need to know. And I would say in the end, it's kind of asking the right questions that kind of get you motivated to go in the right way. And I found that just to be a fascinating part of my journey and something I'm thinking about all the time. So, and I'm very fortunate. My wife understands science, likes science, and you know, when I'm off thinking by myself, you know, not paying attention to anyone, she understands that and can value that. I really appreciate that.
Thank you so much, and again, like a huge thanks for your time. And like I said at the start of this conversation, I'm very honored to be able to have conversations like this with with uh, especially like Nobel laureates.
It was a real pleasure, and I enjoyed your questions. And I always learn something from my podcasts. A lot of things I've already talked about before, but I always learn something and, you know, find it to be a great experience. And I hope that people watching this can enjoy it. And I hope that motivates them to do science better.